Okay, great. So, welcome to week 7 for the live discussion session for the reinforcement learning course. So, we are halfway down the course. It's a 12-week course. We have completed till week 6. I think the content for week 8 is also out. So, today we'll be discussing the content for week 7. I hope so far what we have done, everyone is clear with whatever we have covered so far. If not, you can always unmute and ask me. I'll be happy to explain anything that you haven't understood in the past discussion sessions. Okay. So in week 7, my target mostly would be last week I had explained about dynamic programming, about the Monte Carlo methods, and about temporal difference methods. We stopped with the temporal difference control part. Uh, Today, I'll start by explaining about Q learning and SARSA, which are two TD0 control methods. Then we'll look at two example codes for having a clean understanding of what Q learning and SARSA is all about. And towards the end, I'll motivate and introduce about eligibility traces and how uh, it provides some sort of a neat mathematical formulation to regulate between to regulate and use the advantages of TD0 as well as Monte Carlo. We can leverage the advantages of both and kind of regulate the parameter uh, to achieve those things. Okay. So if in case what I have just said to you is not clear, please hold on. I'll make it clear as we go on with the lecture. Okay. So please let me know if the audio gets disconnected in between or you can't see. Okay. So we'll begin. So last time we stopped with TD0 control, right? We stopped with TD0 control. So quickly before going, can anyone quickly tell me what a temporal difference, what the TD method is about? I'll start writing. If meanwhile somebody can unmute and let me know, so I know you have understood. Okay. So TD method stands for temporal difference method. We have seen that whenever we are doing something like value iteration or policy iteration, we need a complete access of all the states in the state space present to be able to make one update in one iteration. Okay. But what happens is, in order to have a complete information of the state, we need to have an idea about the state transition probability, the uh, which is the probability model of the state. Also, we need to have some idea about the policy pi. And based on that only, we can make updates on the value function and do it iteratively. Imagine if if we want to make some sort of a sample update, okay, let's say instead of having a complete knowledge of the state transition probability, let's say we do it the original way of expectation, wherein we just sample certain experiences, go till we reach the end of the episode, and only once we reach the end of the episode we encountered the full return GT, and then we come back and update the state. Okay, so that's the Monte Carlo method. TD method somewhere lies in between. So what the TD method does is it does a one step sample. So that means given state S, I will take action A, reach state S prime. Okay, I should draw this bigger. Given I am in state S and I take action A in order to reach state S prime. Okay. So this action A that I took need not be a part of any state transition model or any policy that I'm following. It could be any sample action that I took. So all I'm doing is I'm taking one step sample, and in addition to it, I'm doing a bootstrap. So what it means is uh, based on this one step sample that I do, I go back and update the value function based on the value function I encountered at state t plus one. Okay. So just to write it down, uh, earlier in Monte Carlo, your complete return looks something like this. So you have rt plus 1 plus gamma rt plus 2 plus gamma square rt plus 3, and it goes on till infinity. If the episode is an infinite horizon episode, it goes on till infinity. Okay. And if I want to write it compactly, I'll write it as t goes from 0 to, sorry, I goes from 0 to t minus 1, which is gamma I minus 1 r of I. Okay. So this is what the complete return looks like. Okay. So this, we are considering that the episode ends after time capital T. So the episode has a fixed horizon of time capital T. Okay. Now this can also be written as r of t plus 1 plus gamma gt plus 1. Okay, because anything after rt plus 2, if I take the gamma outside common, whatever I have left will be considered as the return at time t plus 1. But what TD tells me is, because I am not trying to use Monte Carlo when I have to go till the end of the episode, and instead of using gt plus 1, which is the complete Monte Carlo return, what if I somehow truncate this return at time t plus 1, and instead use some sort of approximation, or some sort of a heuristic, or some sort of an approximation that more or less represents what the return would be. And eventually, all I need to do is I need not go till the end of the episode. I just need to go up to time t plus 1, get the reward for time t plus 1, and whatever update I have, whatever approximation I have for gt plus 1, I use that and go back to update my previous value function. Okay. So it turns out one good way to do it is like this. So this can be written as, this is approximately r of t plus 1 plus gamma. So instead of the gt, I'll replace it by the value function estimate. Okay. It turns out, my v, if I look at the definition of my value function v, my value function v is nothing but the expectation of gt starting from state s. Okay. So looking at that kind of a definition, this kind of approximation is some sort of an over estimation, so as to say, because I am taking some kind of an approximation. I don't have access to the exact sample, but I am somehow making an estimate of what the return could be. Okay, so I replace gt of 1 with v hat of st plus 1. So once I do that, my update, so whenever I'm trying to incrementally update my value function, incrementally trying to update my v function, so this is how my v update looks like. So I have my v update of new at state s is my v update of old s plus alpha times I have rt plus gamma v hat of old. This will be at state st plus 1. Okay, because I'm using st plus 1, so here this is for state st. Okay, and then is subtracted by v old of state st. Okay, so this is an important equation for TD update. We'll highlight this. So this method is known in literature as TD0. Okay, and the term that comes inside the square bracket here, you can represent it by delta of t. So this term that comes inside the square bracket can be represented by a variable delta t. It turns out it has a very special name. This term inside the bracket is known as the TD error term. Okay, so look closely. This term over here that I have just enclosed within curly bracket represents some kind of a target that I want to achieve. Okay, so imagine I am in some state S. Let's say RT plus gamma V old ST plus 1 is some sort of a target that I want to achieve. And to achieve that target, I want to see how close my old estimate was with respect to the how close my current estimate is with respect to the target function. And based on that, I just update the equation for the stochastic averaging for the value function, and this is where I end up with the equation. So this was all discussed last week. If you have any questions till here, please feel free to ask. So this is in short what TD method is about. You are trying to go one step by taking a sample from state S, and after you go one step ahead in time, you basically do a bootstrapping so that you use v old to update v new. So this method is known as bootstrapping. So you are going one step ahead in time. Maybe this should be r of, yeah, this should be r of p plus 1. Okay, so what this tells me is that given in state st, i I have an old estimate of the value function for all the states at time t. So let's say I want to update that particular value function. So what I'm trying to do is, if I go ahead one step in time to that particular state, I am looking at v old at time st plus 1. So I am not exactly updating the value function. I am looking at the state value at time t plus 1 using the old value function estimate, and I use that to update my new value function estimate. Okay, so this is some small thing that one needs to keep in mind when we are looking at TD0. So this is TD0. So this gives me a method of estimating the value functions for a particular state. Now let's say I want to look at the control aspect of TD0. Okay, so when I say control, so TD0 gives me a method to estimate the value function. Control sort of gives me a method to recover the policy based on the value function. So the value function is a method of estimation and evaluation of a policy. And then in order to extract that policy out, we need to look at control. So far, we have looked at the control for Monte Carlo. Okay, so the idea behind control was that instead of using a value function v, we simply go with the q function. Okay, so instead of using value function v for control, we use the q function. And the reason we use q function is that because the optimal policy, or rather the policy here, it depends on what q you are using. For a normal q function, the optimal policy can be recovered by simply taking an argmax over all qs of 1. By doing that, I can recover the policy, but the same cannot be done whenever I have a value function. Why? Because along with that, I also need to have an idea of the policy and the model. And turns out the main reason uh, to why we started doing Monte Carlo in the first place is we wanted to remove the dependency of the model and the state transition probability when we are doing any estimation. Okay, that's why v function, the v function doesn't work well whenever we are trying to do some sort of a control over here. So in order to deal with control, we always look at the q function. Okay, so going back, so the update rule that I had written for the value function v, for the v value function, I'll simply write it for the Q function. So the update rule looks like this. So instead of state st, we also have to deal with action 80 at that particular instance. So which is okay. So this is how the control equation. This is how the control equation looks like for a naive TD0 methodology for a naive TD0 control part. So I'll just highlight this. Now look carefully. One thing you'll ask me is, if I go back to the last slide, okay, if I go back to the last slide here, sorry, here in this particular step, I had replaced the target. So I had replaced my my GT plus 1 with the value function at state ST plus 1. But here, if I go to the Q update, here, you will see that I replace it with the Q function instead of the V function. You might ask me why this is so. Okay, so originally this should be the V old ST plus 1. Okay, as per the update rule that we had defined in the previous slide. Okay, but turns out this is also some sort of an approximation that I'm taking. So if I fix a policy pi and I get the expectation, so this is nothing but so for a fixed policy pi, my expectation of the Q value eventually would yield me the uh, value function. Okay, so assuming that the policy pi here is fixed. Okay, so all I'm trying to do is, instead of taking the expectation, I take a sample of that expectation. Okay, and turns out if you this also serves as a good estimation for computing, for updating the Q values in time. Okay, so now all I need to do is, once I have this kind of an update rule, let's name it equation number 2. Once I have this update rule, all I need to do is I learn the Q values iteratively for each ST AT pair. Okay, for each state action pair, I learn this iteratively by being greedy with respect to Q of S. Okay, so you can think of it like this. So I start with some initial estimate of my Q values. So let's say I initialize my Q of 0, which is some initial estimate, some arbitrary Q0. Okay. Then I do one step update of this for each state action pair in the environment. I get some Q new value. I keep doing it again. I keep doing it again. And turns out if I do it some large number of time, I'll eventually converge to a fixed point here, which would give me my Q new. And I say that, okay, after doing this many number of trials, I eventually arrive at the Q value for that particular state action pair. And then once I have that particular Q value, I just behave greedily with respect to that Q value to recover the policy pi. Okay. So this is also known as a naive TD0 control method. Okay. So this is one way to deal with control when we are looking at TD0. But turns out there are also other ways. There are two other ways wherein you can use a slightly modified control variant, and this gives rise to very interesting learning algorithms. Okay, so we'll quickly look at it. Cool. So, okay. So earlier in the knife part, the way I estimated this Q, ST plus 1 and AT plus 1 was by fixing policy pi. Okay, here I fixed my policy pi. Okay, so eventually the next action that I'll get, the action AT plus 1 that I'll get it according to the policy pi that I'm following. Okay, so instead of putting that kind of a constraint, how about what if we deal, uh, I mean, we remove that particular requirement. Okay, so we'll say my queue update looks like this. Okay, so everything remains the same. Okay, everything still remains the same except for one small change that I did here. The action A of t plus 1, now I'm no longer sampling it, or I'm no longer taking it on fixing a policy pi. Okay, so here this action A t plus 1 is some sort of an exploratory action. It need not necessarily come from a policy pi. And turns out this kind of an exploratory action that you keep on taking to obtain a Q value can lead to some interesting learning behavior. Okay, so let's look at it. So maybe I should highlight this first because this is an important equation. And we'll call it equation 3 for today. Okay, so let's say we define the algorithm as follows. You start with arbitrary Q. You start with arbitrary Q. Then pick a state has not and take time t is equal to 0. Then pick action AT in ST, and this is done according to your Q value you have. Okay, so according to the Q value that you have for that particular state, you pick action AT, and you do that by using any sort of exploration strategy. Okay, so one good exploration strategy you can always use is the epsilon greedy strategy. Okay, so you always select an action which is by being greedy with respect to the Q function with probability 1 minus epsilon, but with some small probability epsilon, you select some random action which is not according uh, to the Q function. Okay, so epsilon greedy is one such mechanism. You can always use UCB1 or softmax algorithm. Any exploration strategy should do the trick here. Okay, so you pick action AT in state ST according to QST. Next up, what you do is you apply AT and sample S of t plus 1 and R of t plus 1. So once you have selected the action that you want to take, the action in the previous line we had selected to be 80. Once you have selected that particular action, you apply that action in the environment and sample the next state and the reward on taking that particular action. Okay. So once you apply that action, you get your state st plus 1 and the reward rt plus 1. Once you have done that, okay, once you have sampled s of t plus 1, now again you pick action at plus 1. Okay, and this is according to the same q function that I was using for st plus 1, and you use some similar exploration strategy, be it epsilon greedy, be it UCB1, or any known exploratory algorithm that we have seen in the bandit literature. So once you have done that, now you apply this particular update rule. You apply this update rule, and then you increase time with t plus 1. Okay, and you keep doing that until you get some convergence in the q value. Okay, so we'll go back to the beginning. I start with some arbitrary q function. I select state S0 at time t0. I first pick action AT, because for q function, what happened whenever I'm trying to evaluate a q function, I first pick action AT. I don't have a choice with that. Whatever is the action I have to take that particular action. And thereafter, I behave optimally. Okay, this is what my q function tells me. So I pick action AT. I apply that, get the new state. And the next action that I have, that is also sampled, or that is also picked according to the q function. I no longer am fixing any policy pi. So this particular action AT is sampled from this q function. Okay. So you are also taking the next action into account, and then you increase the time. You uh, go back. So here what you are seeing is my action AT. Here my action AT is sort of fixed. Okay. This is how I'm looping around. So I am at time t plus 1. The way I loop around is I go back. I see that my action AT is fixed, but once I apply that particular action, I might sample some new state st plus 1 and rt plus 1 because of a stochasticity in the policy that we have. Okay, so that's why even if I fix the state st and the action at, whenever I keep sampling that particular action, I get some new estimate or some new st plus 1, rt plus 1, and accordingly my at plus 1 also changes. Okay, so once I do this iteratively, I get a q value function which is fixed for that particular stat. Once I've done that, I go back, I select some other state, I pick some other action, and do the repeat this process. Okay, so you can see that the policy, in order to evaluate a particular state action pair in this particular function, I have to be inside the policy. I have to stay within the policy and also estimate according to that particular policy in order to get an estimate of the new q value. Okay, so I'm always staying inside the policy. So this type of an algorithm is also known as an on policy algorithm. That means I remain inside the policy, use the stochasticity that the policy has in mind, take multiple exploratory actions, and arrive at some q. And that's how I update my q value. Okay. And turns out, let's say this is my epsilon greedy. Okay. Let's say this exploration strategy is epsilon greedy. Let's fix it. Okay. We say my exploratory strategy is an exploration strategy. So it turns out that in order to make this algorithm converge, so what I have to do is I have to decrease two parameters. First, I have to decrease the exploration as in when the time keeps on increasing. Okay, so I have to decrease the epsilon in the exploratory state, and also I need to decrease the alpha, which is the step size parameter that I'm taking. So for convergence, we decrease uh, alpha and epsilon. Okay. So this particular algorithm has an interesting name. Okay. So this algorithm is also known as SARSA. Okay. And the way this name is derived is, so it takes into account the state as, okay, different color. So where this algorithm name is derived is, you take state st, you stay for state st and action at. I sample a reward, sample the next state, and also take the next action in order to update the Q value. Okay, so the SARSA stands for state, action, reward, next state, and next action. Okay, this is how the name is derived. So I hope you people are clear with uh, the SARSA algorithm and how it is different from the knife queue control that we had looked at. In knife queue, what I was doing is I fixed the policy pi. Here, instead of fixing the policy pi, I am taking an exploratory next state action. Okay, and this is how for convergence we need to tune the parameters alpha and omega. Okay, so this is one method for which TD0 control can be used. Another way, okay, another method in which you can deal with something similar. Okay, I'll write it down. So my Q STAT all of it is similar, and okay, this will be equation 4. This is another method. Okay, now notice what I did differently here. Okay, in order to update the target, I am no longer fixing the policy pi, neither I'm taking any sort of exploratory action. Instead, what I'm doing is at state st plus 1, I'm taking the optimal action over here. Okay, so that's why I have this max a prime term. So look carefully, equation 3, and look carefully at equation 4. Okay, so what equation 3 tries to solve, if you recollect, what equation 3 tries to solve is the Bellman equation, right? What equation 3 tries to solve is the Bellman equation, and what equation 4 tries to solve is the optimal Bellman equation. If you recollect from the discussion we had in the week 5 class, okay. So my Bellman equation eventually will give me a policy pi, but my optimal Bellman equation will give me the optimal policy in that particular, for that particular environment. Okay. So here we are trying to solve for optimal Bellman equation. So instead, at the next state, at state st plus 1, I no longer take any exploratory action. Instead, I behave optimally thereafter. Okay. Only the first action I take is according to what is given to me. I don't have any choice in taking the first action 80, but I behave optimally thereafter. Okay. So algorithmically, you can define it as start with arbitrary queue. Okay. Then pick a state S0, fix time t equal to 0. Then pick at in st. This is according to my queue function. Okay, so you have again your exploration strategy. Do that, and in the end you apply at and sample st plus 1 and rt plus 1. Okay, and thereafter you do this update. Here also you did this update from here, and then finally you update your time and then go back. Okay, what this gives me is that for a fixed state action pair, I take action for a fixed state st, I take a fixed action at, and thereafter I always behave optimally. Okay, so turns out here the way I sampled at, this was sampled according to some exploratory strategy, but turns out the advantage or the power this method has to offer is that even if I don't use any exploratory strategy, even if I pick any arbitrary at state st, I will still converge to the optimal policy. Okay. The reason why we are dealing with some exploratory strategy is that because for a problem statement that we have in mind, let's say we want to still be in that particular trajectory while we are dealing with it, and instead not deviate around at some other place. Okay. So turns out even if you don't use any exploratory strategy, you will again converge to the optimal queue function. And yeah, but just that by using some exploratory strategy, you are just speeding up the process. Okay, but this is not a necessary condition whenever we are looking at this kind of an update rule. Okay, now notice that here, in order to update a particular state action pair, I need not take that particular action and do any sort of exploration in order to go ahead and make an update for the Q value function. Okay. I no longer have to be on the policy to make any updates to that particular Q value. Okay. I can always behave optimally after taking the first action at and use that iteratively to get to the optimal Q value. Okay. So this class of algorithm is known as an off policy algorithm. Okay, this is something we had also seen in Monte Carlo. So in off policy algorithm, you have a behavioral policy and you have an estimation policy. Okay, so if you notice equation 4 closely again, you will see that while you're trying to estimate your QSTAT, this is something that you're trying to estimate, but the way you're behaving is always by taking the optimal policy. Okay, so the way the update is happening is by behaving optimally, but for estimation, you need not have any sort of uh, optimal behavior. Okay, so this some kind of a workaround here. So that's why you see that this update is done in an off policy fashion. Okay, so turns out this method has a name, and this is known as Q learning. Okay, this is known as Q learning, and for convergence, we no longer have to worry about the we no longer have to worry about my epsilon parameter, the epsilon greedy parameter, because even without acceleration, we can still have convergence, but we need to still tweak the parameter alpha, which is the step size parameter. Okay. So we need to cool that down slowly over time in order to show convergence. Okay. So turns out in reinforcement learning, these are two popular algorithms. One is known as SARSA, one is known as Q-learning. One falls in the class of on-policy algorithm, other falls in the class of off-policy algorithm. In an on-policy algorithm, the policy that you will get, the optimal policy that you will be a stochastic policy. The optimal policy that you will get from an on-policy method would be a stochastic policy. Whereas in an off-policy algorithm, you will always get a deterministic policy. Okay. This is another difference between these two class of algorithms. And also in off-policy algorithm, because you're using two different policies, one for estimation and one the uh, for the behavior modeling. So the number of states that you're visiting is much more than the number of states that you would visit if you're doing an on-policy algorithm. Okay, so off-policy algorithm has a higher exploration, but it still gives me a deterministic policy. Okay, so this is the power that Q learning has to offer in compared to any on policy algorithm. But turns out on policy algorithm also has benefits whenever we want to deal with any kind of a trajectory estimation kind of a thing. So behaving with respect to behaving and estimating with respect to that same trajectory also has its advantages. But again, the answer would be it depends on the different kinds of use cases. Okay, but eventually both these methods will give me the optimal Q values. Okay, eventually after trying out everything, the Q values that I'll get in the end will be the optimal Q values. Okay, I mean they should be it should I shouldn't say optimal, it should be epsilon optimal. Okay, we had proved earlier also, right? The value functions that we get on solving the Bellman equation and the optimal Bellman equation, if we use value iteration, we will be within epsilon distance of the optimal policy. Okay, so turns out there is a particular example for this to explain the power of or differentiate between these two class of algorithms. This is known as a grid world algorithm. Okay, so way we define this is, so we have, let's see. Okay, so we have a 3x8 kind of a grid. So here we'll define the starting position to be SG, and that is a cliff here when we want to go from the start to the goal position. So if you fall into the cliff, you die. You again go back to the start position, and you get a reward of -100. Rest everywhere you keep rest everywhere you get a reward of +100 everywhere else you go. Okay. Okay. So this is a 4x8 grid. Okay, so this grid is this kind of a world is called a cliff world. Okay, so this is a popular example that you will find if you look at any online available reinforcement learning class. People more or less go back to this kind of an example to show the difference between SARSA and the Q learning approach. Okay, so this is a cliff world. Okay, now if I were to implement Q learning and SARSA to this cliff world example, turns out the policy I'll get for Q learning and the policy I'll get for SARSA would be very, very different. So my SARSA should learn a policy such that from here it goes up, it goes here and reaches here. Whereas my Q learning would learn a policy to take this particular route. Okay. And there's an interesting reason why this thing happens. Okay. Because my Q learning learns a deterministic policy. So there is no scope for exploration. Okay. So the policy that it will learn without keeping any sort of exploratory behavior in mind. So all particular action that it will take will be taken by behaving optimally. That's why the policy that it will try to learn the shortest path to go from the start to the goal position. Whereas in the case of the SARSA, we always have an exploratory behavior. Okay, whenever we want to sample the next particular action. So now turns out if I am at this particular state, if I'm at this particular state, so one wrong exploratory action can lead me to going down and falling into the cliff, right? And similarly, even if I'm in this particular row, one wrong action, or rather, it takes me only two exploratory action to go and fall into the cliff. Okay, so taking that exploration into account and understanding that the world is stochastic, so my SARSA gives me a stochastic policy, keeping in mind that there is a possibility of me exploring and falling into the cliff. So the kind of policy that SARSA learns, so should mention my blue curve is SARSA and my green curve is Q learning. Okay. So SARSA takes into account the stochasticity in the world and tries to understand that behaving in an exploratory fashion can sometimes result in me falling into the cliff. So the type of route I'll take should be some kind of a safer route so that I try to steer further and further away from the cliff. Okay, so this is the policy that my SARSA kind of gives me. Whereas Q learning, since it gives me a deterministic policy, it doesn't take into account any sort of non-greedy action that I can have in that particular state. So therefore, the policy that we have is a deterministic policy, and it's optimal. Okay, so this is what Q learning and SARSA gives me. Now we'll take a short break. Maybe we can see an implementation for Q learning and SARSA on a Python program that we have. Okay, so that we clear the concepts for SARSA and Q learning. So please let me know if you can see my screen. Are you guys able to see my screen? Please comment.
Yes.
Okay. So I'll just share this here. I'll also share it when I upload this to YouTube, this whole Python code.
I
So
have
this,
I have
yeah,
one doubt.
Okay,
So in the PPT, you show that okay, SARSA will explore more,
correct.
but SARSA is on policy algorithm.
Correct.
So on policy means that will not explore that which I think, according to me. Off policy means that is looking at the previous decisions, then taking the decision. I
No.
don't know where I'm wrong.
Okay, so off policy method, what it does is it uses a different policy for behavior and a different policy for estimation. Okay, so if you're looking to solve the optimal Q function, okay, so if you're looking at Q learning, I am trying to uh, find the Q value for each particular state action pair. Okay, but the update that is happening, this that is happening based on the optimal action that I will take in that particular state action, right? If I go back to my Q learning definition, so I always have RT plus gamma max of A prime QST A prime. So at state ST plus one, I am always looking for the optimal action, optimal next action, rather I should say. So even though I am trying to estimate the Q values for each state action pair, what the way the update is happening is it is always taking into account the optimal action after taking action AT, and based on that the update rule happens. So that's why we call it as an off policy mechanism. The reason we say that an off policy method uh, has more exploration is because since we have two different policies, the number of states that these two policies will visit would be more. But an off policy algorithm also, the any off policy algorithm, the policy that it gives me is necessarily a deterministic policy. Okay, this is also you need to keep in mind. So when I say a policy is deterministic, what I mean is for a given state S, only one action has the probability of one, rest all action has probability of zero. So there is no distribution for the actions. There is one particular action that is being taken with probability one. Rest all other actions have probability zero. So this is what my off policy algorithm gives me. Whereas if I look at an on policy algorithm, for each particular state, I have a probabilistic way to sample the next action. Okay, so I have some sort of a distribution, some sort of a policy model from which I can sample my next action. And because I'm sampling from a distribution, there could be some action which is non-greedy, but I am still able to sample uh, because I am following that particular distribution. I can always sample some action from the head or tail of the distribution, and that's why we call it as a stochastic policy that we have. Uh,
Okay. Just I'd want to know one more thing, Manav.
mhm,
Uh, Means if we have off policy algorithm, then
mhm.
what is the relation between off policy and exploration in on policy and exploration? Are they means related to each other? Off policy have less exploration, like Q learning is off policy,
Hmm.
that is exploring less. Is
That
there?
is that is exploring less. I am not using explicitly any sort of exploration strategy to update my queue function. I'm not using any epsilon greedy or UCB1 to update my queue function later on.
Okay.
So if you okay, let me just share back my screen again.
So actually, I
Just
was actually I was having a doubt in that only.
okay.
Like Q learning, we take the shortest path. So
Q in Q learning, you take the optimal path, which is the shortest path.
okay, we take the optimal path. That's why
Yeah,
that is the shortest path.
correct.
So off policy algorithm means always will be taking the shortest path. That means
Not necessarily, not necessarily. In Q learning, you are taking the optimal path. Q learning is one sort of off policy algorithm.
okay.
Okay. See, in Q learning, you're solving for the optimal Bellman equation. So the policy pi that you get on solving the optimal Bellman equation would be pi star. That is the optimal policy that you are taking. So if you see this example, this green curve is the best, is the optimal policy. If I look at it from a naive lens, if you and me are looking at it, we
Yes.
both can see that this is the optimal policy. Okay.
Yes.
And we are taking it in a deterministic fashion. Okay. We need not care if there is like any sort of obstacle is there in front of it, or if there is a wind blowing from the north side, or any stochasticity that comes up later in the environment. My Q learning won't take that into account. Okay, so let's say I have an obstacle somewhere here. Uh, let's say an obstacle appears here after some time, because I say that my environment is stochastic. Okay, so my Q learning algorithm here would take some exploration action because it is stuck. It can't go straight ahead. Okay, so if it takes any random action the because of the obstacle, there are heavy chances that it might go and fall into the cliff in this particular state. Whereas if I had used Sarsa kind of have a distribution of the actions. Okay, while my Q learning gives me the best possible action, my Sarsa gives me a distribution of all the actions that I can take in that particular state as. So let's say my first best action is not feasible for me if I'm following a Sarsa policy. I'll go back and select the next best action. That's why you have a stochastic policy, right? So any random occurrence of any obstacle, or let's say there is a wind blowing or some changes happen in the environment, then Sarsa tends to work better because it learns a stochastic policy.
Okay. Okay. Thank you. Thanks, Manu.
Okay. So, so this is a very simple implementation of the Cliff World example. I have implemented it using Python. So you just go here. You What I've done is I have defined a class called Cliff. Okay, so it has the first argument about the init, wherein there are variables like end, position, how the board looks like. Okay, what all variable each board has, then what are the actions that I can take, and if I take that particular action, where my next position would be, and so on. And if my position is equal to G, then it's the game ends on reaching the goal. Otherwise, if I fall in a cliff, then the game ends when I fall into a cliff. And the reward is that if I if I reach the if I am at any other state, I get a reward of -1. But if I fall into a cliff, I get a I get a reward of -100. And this is a function to make a plot and show how it looks like. Okay, that was the class for cliff. This is another class for agent, wherein you are taking the cliff into account. You define the actions of the agent, you define the states. So whatever state I have, I'll store it here, and correspondingly store the corresponding up, left, down, up, left, right, down actions. Okay, then I define the exploration rate, which is zero point 0.3 here. My LR, which is alpha, is 0.1. So here, since I've made SARSA equal to true, I'll be using the SARSA algorithm. If it's false, I'll use Q learning. Okay, and this is how the choose action step happens. So this is an epsilon greedy strategy. So this is used both in Q learning and SARSA, but Q learning is not a necessity. The only reason we are using epsilon greedy in Q learning is because we want to kind of reduce the time for convergence here. Because eventually, even without an epsilon greedy strategy, I'll still end up getting the optimal policy. Okay, this is the reset part for the particular agent class, and this is the play. Okay, so for each, so so I do this for 10 number of rounds. I for my current state and the current reward, I take the next action and uh, based on according to the Q value, and then if it's SARSA, I use the update rule for SARSA. If it's Q learning, I use the update rule for Q learning. And lastly, I do reset. And this is a function to show the route that we followed. Okay. So this is like a base class implementation. So it has all the information that we have for the agent class, for the cliff class, and for the plotting part. Okay. And this is the SARSA implementation. So if I print this here, so here my agent has an exploration rate of zero point 0.3 in SARSA, and I'll be playing 5,000 rounds over here. Okay. Okay. So what it gives me is that for each particular position, it is giving me the action that my SARSA would follow in that particular. It would follow in that particular state. Okay. So if this state is 0, 0, this is 0, comma 1, 0, comma 2. So the first index represents my row. This is a 0th row, 1th row, second row, and third row. Similarly, this is the first column, second column, third column. So this position is 3, comma 0. Okay. So for this position, so for this state, I should take the up action. At 2, comma 0 here, I should take up action. For 1, comma 0, I should take up action. When I reach 0, comma 0, I should go right. Then I go right here, here, here till I reach here. Okay, 0, comma 9, and then I take a down action. Then again I take a right action, and then I go down, down. Okay, so this is something that my SARSA policy has learned in this case. Of course, if I change the value for the exploration, the policy that my SARSA learns would be different than what it has learned now. And the exploration rate strategy and the learning rate, both these factors determine the policy that my SARSA learns. So this is what it learns, something which I have, something which we saw, and something that uh, we expect also. Okay. Similarly, for Q learning, this is how the algorithm looks. So I get a deterministic policy which follows this particular route. Okay. So for 3, comma 0, I take up. Then here I go right, 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 right. And lastly, I go down. Okay. So this is implementation for Q learning and implementation for SARSA. I have shared this code. Another interesting code that I have, maybe we can discuss today. So it's kind of a tutorial that I have. This also I'll share with you guys. So the cliff world was some naive example, right? So we'll look at another interesting example. So let's see. I'll just run this first line. No such file. Okay. Why? Maybe I should restart the kernel, restart the runtime, and see if it works. Okay, so the drive is mounted. I load the drive. Here I'll install all the relevant libraries. This might take some time, but since I already have it, okay, this is executed. I'll import all the necessary Python packages. Okay, now we'll look at the problem statement. Okay, so in this section, we'll implement a tabular SARSA and the Q-learning algorithm for a grid world navigation task. So the environment details are as follows. The agent can move from one grid coordinate to one of its adjacent grids using one of the four actions, which is up, down, left, and right. Okay. The goal is to go from a randomly assigned starting position to a goal position. The actions that can result in taking the action off the grid will not yield any effect. So let's take a look at the environment. Okay. So these are the four available actions, and these are stored as down, up, left, right. And this is how the grid world looks like. So I have created a txt file. So this is how the grid world looks like. This is a 17 cross 23 grid. The reward when an agent goes to a cell is negative of the value in that position in the text file, except if it is the goal cell. We'll define the goal reward as 100. We'll also fix the maximum episode length to 10,000, which means, so if I go to a cell where there is 1, I'll get a reward of -1. If I go to a cell where there is 2, I'll get a reward of -2. Everywhere else, I'll get a reward of 0. But if I go to the goal, uh, the cell which has the goal, I'll get a reward of 100. And we fix that the maximum episode length is 10,000. Now let's make it more difficult. We add stochasticity to the environment. Okay, so in order to truly show the difference between SARS and Q-learning, we need to have an environment which is stochastic. So we add stochasticity to the environment with probability zero point 0.2. Agent takes a random action, okay, which can be other than the chosen action. So with 0.8 probability, agent takes the best possible action, and with 0.2 probability, agent takes a random action. There is also a westerly wind blowing to the right. So there is a wind which is blowing from left to right. So hence, after every time step, with probability zero point 0.5, the agent also moves an extra step to the right. Okay, because of the wind, there is a 50-50 chance that at each time step, the agent can move one extra step to the right. Okay, this is because of the effect of the wind. Now let's plot the grid world. Okay, so this is how the grid world looks like if we look at it from pictorial point of view. Okay, here the green cell, here the green cell is my goal. I want to reach the goal position. These three blue cells here are the starting positions. Okay, the agent can be initialized in any of these three blue cells. So since the agent got initialized here, so this cell became yellow. Okay, so once the agent moves, the yellow block will keep on moving, which will represent the agent. So maybe if I do this again, you see, okay, agent gets initialized here, but it can get randomly initialized in any of the three start cells. Okay, legend. Blue is the start state, green is the goal state, yellow is the current state of the agent. Redness denotes the extent of the negative reward. So here you get a reward of 0. Here you get a reward of -1. Inside you get a reward of -2. Okay. For Q values, we use 3D array to represent Q values. The first two indices are the XY coordinate and the last index is the action. Okay. So I initialize the Q value. All values are 0. So this is the Q plot. Initially, all Q values are 0 and the action it points is an arbitrary action. So it stores three values. It stores the what it stores. It stores the XY coordinate for the Q value, and the last index is the action. Okay. So this is how the Q table looks like. It's a 17 cross 23 cross 4. This thing, 4 3D array. So for exploration strategy, we have two different strategies. One is the epsilon greedy. One is the softmax policy. So So these are the two functions to choose action using an exploration greedy strategy and by using a softmax strategy. So I run this. Next, we implement the SARSA algorithm. Recall the update rule for SARSA. So I have QSTAT is QSTAT plus alpha times RT plus gamma ST plus 1 AT plus 1, where this AT plus 1 is an exploratory action minus QSTAT. So hyperparameters, we have some hyperparameters for the algorithms. Some, which is alpha, which is the learning rate, number of episodes, which is fixed to 10,000, but okay, let's see. Epsilon for the epsilon greedy exploration. So initialize the Q value, which is NP dot zeros. My alpha 0 is zero point 0.4, my gamma is 0.9, number of episodes is 10,000, epsilon 0 is 0.1. Okay, so the reason I've defined alpha 0 and epsilon 0 is because I want to cool down both my alpha and my epsilon for convergence. We had seen, I had mentioned that in the slide, right? For convergence, I need to cool down both alpha and the epsilon. So let's implement SARSA. So this is a function for SARSA. I you might you can take a look at this code later on. I'll just yeah, okay. I'll just make a top view explanation. So I reset the environment for episode in the total number of episodes. So I have running a for loop for 10,000 episodes. I reset the environment. I choose a particular action. My When I do env.step, I get the next state, the reward, and the done value. And then the next action is by using choose action, which is any epsilon greedy strategy that we have. And then this is the Q update equation according to SARSA. Then the total reward step is taken into account. And then my next state and next action becomes my state action. And then if I run this, okay, if I run this, it will take some time. Okay, this is fine. So if I run this will take some time to uh, get the final answer. So I have already run this here. So this is how the policy looks like for SARSA. Okay. So starting from any state, I am always trying to move towards the goal, which is here. Okay. But see, because of the stochasticity here, because here you get a reward of -1. So inside this region, the agent tries to move outside the agent tries to move outside this region and go to the goal. And again here, the agent tries to move outside the region and go to the goal. Okay. So this region is kind of a hot region. So I should try to avoid this region as much as possible. So that's why the arrows are pointed accordingly. Now visualizing the policy. So run this below cell as many times to render the policy. Okay. So maybe I should run this once. But okay. Yeah. So this is being run for 10,000 episodes. Okay. So it takes some time. But see, this arrows are being updated in real time. Okay. So this might be useful for visualization purposes. Okay. So after every say 100 episodes, there is an update for the plot, and you can see in real time how the plots are changing. It will take me around 1 minute to for this to complete. Let's see. Let's wait. Okay, so this is complete. Now we just want to visualize how the policy here looks. Okay, so the agent starts from here. It goes here, here, here. Okay, so this is the sequence of action it took to reach the goal. Okay, if I run it again, let's see if we have something else. Okay, so if it starts from here, it goes here, here, here. Okay, it went inside. Okay, so maybe one more. Okay, start from here. Okay, so here maybe we need to train it for more number of time in order to see that it tries to avoid this region uh, as much as possible, but still it is trying to take some action which takes it further away from these regions, which can result in a negative penalty. Okay, so if I train it more, maybe we'll get some better results. But this neatly models the stochasticity in the environment, because for each particular state I have four possible action, and since I have a probability of action I can take, I sample from the probability and go in any particular direction. Okay, so analyzing the performance, we use two metrics to analyze the policy: the average steps to reach the goal and the total rewards from the episode. To ensure we account for randomness in the environment, say when using epsilon greedy, we run the algorithm for multiple times and use the average of values over all returns. Okay, so they run this experiment for 5 times. So this 10,000 time steps. So I won't run it now, so because it will take some time. But this is how the plot looks like. Okay, so we run this experiment for 5 number of times and we take the average. So this tells me for the number of episodes, the number of steps it took to reach the goal. So initially it took 4,000 steps because initially it hadn't learned anything and it did a lot of exploration. But as and when we reached here, you see there is a neat convergence and it took very few steps to reach the goal. And this is how the total reward looks like. Okay, so you see a neat uh, reward convergence happening at this particular point. So 100 is the reward you get on reaching the goal, and any other place you go, you get a reward of -1. So this is how the metric looks like. Similarly for Q learning, so this is the code for Q learning. It's similar except the update rule is different. And if I do the training, so this is the training for Q learning. You see how the policy looks like. Okay, how the visualization of the policy changes as and when it starts learning. Notice this doesn't at all take into account the stochasticity that the agent can experience while moving in the environment. So you see, it learned the optimal policy uh, in the earlier time step itself, and unless and until there is some drastic change in the environment, it uh, is not updating much. Okay, because the q values that it has learned so far is more or less the optimal value. See, so it will try to take the shortest path in the environment. If that particular grid world was fixed, and if there was no wind blowing in the environment, maybe q and sarsa would give similar policies. But because there is a westerly wind blowing and there is a probability of me taking some random exploratory action, this is how the policy here looks like. Okay, I think this is complete. And let's see the visualization here. So it starts from here, it goes here, 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 and reaches the goal. Okay, it's a very smoother path here because there is no random action that it can take. So here also it goes from here, and it will reach the goal in the shortest path. So it is learning the optimal policy here. See, it is trying to go around because it is trying to avoid this region as much as possible. One more. Okay. So here it is reaching the goal. Fine. Similarly, we are trying to look at the performance metric, which is the time to reach goal and the average reward. This I won't execute now, it will take a lot of time. This is how it looks. Okay, so for Q learning, this is the plot for the number of steps. It decreases as the number of episode increases, and the total reward increases as the reward is increased. Okay, and this is a side-by-side comparison for SARSA and Q learning. So you see that more or less they behave similarly, but it really depends on the use case that people are targeting. So Q learning is like a very popular algorithm in RL, in classical RL literature. SARSA is kind of the second most popular algorithm. But again, depending on the use cases, different algorithms can be used accordingly. Okay. With that, I think we can move ahead. We can close Q learning. We can close SARSA. I hope you guys have clear understanding now of the TD0 methods and Q learning and SARSA. We took around 1.5 hours today here. Okay. If you have any questions, feel free to ask. Otherwise, I'll just move ahead. So I will share screen here and go here. Okay. So next up, we look at an interesting concept. Okay. So this is after we have done TD0, we look at an interesting concept known as eligibility traces. Okay. So we'll come to the definition of eligibility traces now. So we'll look at the concept of eligibility traces. So this is a method which takes me from TD0 to a TD lambda method. So it's a generalization from TD0 to TD lambda. So if you look at Monte Carlo return, okay. So how the return looks like. So if I look at the return when I do Monte Carlo sampling, so I get RT plus 1 gamma RT plus 2 plus gamma square RT plus 3 dot till I reach the end of the episode, which is here. Okay, and I get a terminal reward RT. Okay, so this is the complete return, or you can also call it as the Monte Carlo return. And this is the return that you get only after you reach the end of the episode. Only after you get the terminal return, you sum it all over, multiply it with the discounting factor, and you have the complete future return. Okay. Similarly, for TD, what you're doing is you're only taking R of T plus 1. You're taking one step immediate return, and then you're discounting it with the estimated value function at state ST plus 1. Okay. So you can think of it like I am only taking one step ahead in time, and then I'm back propagating. Okay. So this we'll just represent it by GT of 1. So this can also be thought of as a one step truncated complete return. Okay, this can be thought of as a one step truncated complete return. Okay, now what is GT of 2 here? Okay, from here, if I say my GT of 1 is, I take RT plus 1, and then after that I approximate the later time step reward with the estimation of the value function at that particular instance that I have. What is GT of 2? So here I'll take 2 steps ahead in future. Okay, so I'll take R of t plus 1 plus gamma R of t plus 2, and at step 3 I'll just estimate it with the value function. Okay, so this is GT of 2. Similarly, if I were to generalize it, my n step return GT of n should look like. So basically, I take n step in the future and then I do the back propagation by estimating it with the value function. This back propagation is also known as bootstrapping, right? So you go here, you do gamma R of t plus 2 plus gamma square R of t plus 3, and then you go till you reach gamma n minus 1 R t plus n, and after that you all subsequent steps are approximated by v of s t plus n plus 1. Okay, so this is the n step return. Now this is a picture that I am using from the Sutton and Bartow second edition book. I'll try to just draw it here. So for TD one step, this is how the backup diagram looks. Okay, so this white bubble represents the state, black bubble represents the action. Okay, so I'll only take one sample of the action to go to the next state, and then I'll do an update. Okay, so this is how the one step update looks. For two step, naturally, starting from state S, I'll go 2 steps ahead in time, as in I'll go 2 steps to the next state, and then only I'll do the backup. Okay. Similarly, 3 step is I go here, 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 and here. Okay. Now to generalize it, my n step return is what? I just okay. This is my n step return. I should go here, here, here. Okay. So this is my n step return. And going even further, if I take a t step return, okay, that means if I go till the end of the episode, that many number of steps I do, I eventually end up getting the Monte Carlo return, right? Which is if I reach the terminal reward state, I just do an update till I reach back. This is just copy this here. Okay, so here, this is just the terminal state. Okay. Okay. So you see, we are using a one-step uh, return because we don't want to have the computational use the comput like always taking a Monte Carlo estimation is computationally expensive, and also we cannot leverage the idea of actually using the method of bootstrapping. Okay, we necessarily have to wait till we reach the end of the episode in order to do any sort of backpropagation or any sort of bootstrapping. Anywhere midway, we can't do any sort of bootstrapping. Okay, so this is a backup diagram. So backup diagram. Fine. So now, it's the time. Okay, it's 7:40. Okay. So now we'll look at two different types of learning. So it's online versus offline learning. Okay. Notice that this is different from what we have been hearing so far on policy and off policy. Okay. Here, online and offline simply means like if I'm following a particular trajectory, do I update it while I'm following that particular trajectory, or the updation happens only after that particular trajectory is complete? Okay. So for online, you have multiple state visits are averaged for online case. That means if I am following a particular policy, if I'm following a particular policy, and if I keep on updating for each number of time step I visit that particular state. Sorry, just a second. Yeah. So if I make multiple visit, yeah. So if I make multiple visits to the same state when I'm following a particular trajectory, so a multiple state visit to that thing gets averaged. Okay, in an online in the online learning case. So when I say this is average, I say that I mean that this is the average of the value function. Okay, in the online case. And in the offline case, what you're doing is you wait till end of episode to make updates. Okay, this is a small uh, definition one needs to keep in mind. What is online learning and what is offline learning? So let's say I define my delta VT ST. I define my delta VT ST as alpha times GT of n of VT S of t plus n minus VTST. Okay, so here, if I'm just looking at the error term when I'm doing the stochastic averaging, so the target term here, so this target term over here, this particular target term over here, if it's TD learning, I only look at GT of 1. That means I do RT plus 1 and then I take gamma of BST plus 1. Okay, for an n step return, I replace it with the appropriate return for that particular return case. Okay, and then for online update, this is how online updating looks. So my VT of 1 S is equal to VT of S plus delta VT of S. This is for all S belonging to the state space. Okay, so this is called online updating. Maybe I should highlight this too. Okay, so this is online updating. Okay, for offline updating, so this update doesn't happen at each time step. So my VT of VT plus 1S is equal to VT of S for all time t, which is less than capital T, which is the length of the episode. And this is true for all states S in the state space. The update happens only when the episode is completed. So my VT of S is V of capital T minus 1 S T02 T minus 1 delta VT of S. Okay. And this is also true for all states S belonging to the state space. Okay. Now notice here, this T minus 1, this capital T minus 1 need not necessarily mean that one is not here. This T minus 1 doesn't denote the one step time before I reach the end of the episode. Rather, this T minus 1 is talking in terms of episodes. Okay. So T minus 1 here simply denotes the previous episode, not one step prior to reaching my time capital T. Okay. So this is a notational difference here. Okay. And here I'm doing a summation over here. One would ask, why not an averaging? Okay. Because whenever I do an average of the value function, why not do any sort of averaging? Okay. So the answer here is the you just look at equation 5. Okay. So equation 5 is a formulation or is a way for stochastic averaging. So when I write alpha, so this alpha takes into account that averaging which is happening over here. So I did not explicitly do a 1 over n or 1 over t whenever I am doing the summation. The mathematics in equation 5 is defined in such a way. So if you go back to the definition of stochastic averaging that we have been looking at since week 2, week 3, you will see that this is already taken care of in this particular formulation. Okay, so this is known as offline updating. Okay, so it's a method of updation. How policy can be updated. Okay, now one might ask is, we have defined GT of superscript 1, GT of superscript of 2. Okay, or rather we have defined GT of n. Now the question is, what value of n is ideal in this case, right? How do you decide what kind of n is ideal in this case? Okay, or how do you leverage the uh, benefit of the one step return compared to the two step return? It turns out there are certain applications, there are certain arcade games where a three step return works better as compared to a one step return. In some example, a two step or a five step return works better than a one step return. Okay, so how do we know that what kind of n or what value of n is ideal for our case? Or rather, the question is, which states here are eligible for updates? Okay, so this deals with a method known as eligibility traces. So this comes from uh, behavioral psychology. What it tells me is that, so let's say this is our brain and we are visualizing some particular state multiple number of times, and based on the number of times that particular state is experienced, times of visit, based on the number of time a particular state is visited, our brain generates some kind of a stimuli. Okay, so let's say this is a place where state S was visited. My brain creates some kind of a stimuli. Here, my brain creates some kind of a stimuli. But since we are moving here ahead in time, okay, and let's say this is the stimuli. Okay, so this stimulus decreases. Okay, once that is not updated. So this is how the stimuli decreases. Let's say this is some exponential drop that is happening. And here this is decreasing like this. Okay. And let's say at this time t, I want to update that particular state s. Okay. So I need to take into account what is the stimuli that was generated. So the closer in time a particular stimuli was generated would be more likely to be updated than some sort of a stimuli or some sort of an outcome that happened way before in time. Okay. So this is some kind of an idea. So think of it like this. There is a certain outcome which is happening whenever I am taking some sort of a state action trajectory. There are certain outcomes that are happening. So if certain outcomes are spatially closer, okay. So if I am spatially closer to outcome, then I already have my discount factor to take that into account, right? This takes into account the spatial closeness of an outcome. What outcome occurred previously in space and what outcome occurred more recently in space. Okay. Now, if I want to define temporal closeness, so a temporally closer to outcome, we need to uh, define something known as eligibility traces here. Okay. Notice that this is somewhat related to the credit assignment problem, which professor had discussed in week 1, but it's not exactly the same thing. But just to uh, make some sort of a connection, this is somewhat related to credit assignment problem. Credit assignment problem. Okay, but it need not be the same. Okay, so turns out to define eligibility trace mechanism, there are two kind of viewpoints a person can think of or a person can look at. So there is a forward view and there is a backward view. Okay. So when I define TD lambda, so did I define TD lambda? No, I haven't. So when I define TD lambda, there is a forward view of looking at it. So it's a neat mathematical trick. So this is useful for understanding and having an intuition of what really is happening. And there is a backward view. So it's kind of a mechanistical view or a less theoretical view, but it's more practical in nature. Okay. So we'll look at both these approaches, and turns out that both these approaches, uh, if you look at both these approaches together, both these approaches have some sort of an equivalence. Okay. So we start first with the forward view of TD lambda. This is forward view of TD lambda. So let's say, so for forward view, I'm dealing with something known as lambda return. Okay. So let's say I define GT of lambda. So let's say I want to leverage the benefit of a one-step return backup and a two-step backup. Okay. So I'll do something like 0.5 GT of 1. This is a one-step backup. And then 0.5 of GT of 2. Okay. But now you'll ask me, like, why stop at a two-step return? Okay. Why not move ahead? So we'll say, okay, we'll do 0.33 GT of 1 plus 0.33 GT of 2 plus 0.33 GT of 3. And you can extend it further and further. But okay. And you can say, okay, if I do an average over all different types of backups or all different types of returns that are possible, you have a good way of getting a weighted average of the n step return. You can think of it as a weighted average of n step returns. Okay, heuristically, there is a way to define it. Okay, if I extend it, why this heuristic comes up in the forward view, then it might seem some sort of it might seem somewhat arbitrary, but turns out this kind of a view has like if you look at it from the backward view of TD lambda, this kind of viewpoint actually makes sense. So this heuristic is taken just to ensure that there is an equivalence between the forward view and the backward view. Okay, so you have GT of lambda. So what I'm doing is I'll take GT of 1, then for GT of 2, I'll uh, weight by a parameter of GT2 plus lambda square GT of 3, and so on till I reach the end. Okay, so this lambda is a value between 0 and 1. This can also be 1. Okay, this is between 0 and 1. Notice if, okay, now all the, so this is a weightage, okay, for each lambda. So if I sum up all these lambdas together, all of them should sum up to 1. Okay, now you think of it like an infinite GP. So if I have all different lambdas, I'll just do a summation. It's like summation over lambda k. But since this is an infinite GP, if I it's an infinite GP, so this should give me 1 over 1 minus lambda. This is just a summation of an infinite GP, right? So because I want this to be 1, I'll just multiply it with a normalizing factor. So if 1 minus lambda is multiplied, eventually the summation of all these coefficients sum up to 1, right? So that's why we have this normalizing factor. And let's say I don't do an infinite step return. Okay, so based on this formulation, I keep on doing an infinite step return. But let's say my episode terminates at time t. Okay, and after that, I don't need to look ahead that much in ahead into future. Sorry. So I have n equal to 1 capital T minus T gamma n minus 1 GTN T minus 1 GT. Okay. Uh, okay, how do I define this? Think of it like this. Okay. Let's say this is some particular episode. Okay. It starts at time t equal to 0 and runs till time t equal to 100. Okay. Just an example. Let's say there is an episode that starts at time t equal to 0 and runs till time t equal to 100. Okay. Now let's say I'm taking a weighted average. Okay. I'm taking a weighted average over the n step backups. So let's say I'm looking at a 10-step backup. Think of it like this. I'm looking at a 10-step backup. So till episode t equal to 10, I'll add episode t equal to 0. I'll look ahead till episode t10. Okay, and then update, go back and update t1, t0. For t1, I'll go till t11 and so on till I reach t equal to 90. Okay, once I reach t equal to 90 at this particular state, if I look 10 step ahead in the future, I'll reach the terminal state because at t equal to 100, the episode terminates. So eventually the reward I'll get will be the terminal reward. Okay, so since this is a terminal state, after time step t equal to 90, whatever return I'll get that leads me to the terminal state will be equivalent to my Monte Carlo return, right? After t is equal to 90, I don't have to do any approximation by a v function beyond a 10-step backup. Okay, that means for an n-step backup at time instance capital minus n, beyond that point, every other return is equivalent to a Monte Carlo return. Okay, so this is what this formulation is saying. So if I'm doing an n-step backup, okay, and I'm looking ahead for a time horizon t, so this is only valid till I reach time t minus capital T, because beyond that point, after that particular point, all the values that I'll have will be all the returns that I'll have will correspond to the Monte Carlo return. Okay. So this is a separation that we have here. So maybe we'll number this five, sorry, six. So this is the lambda return formulation. Please stop me if you have any questions. Okay. And notice, sorry, equation 6 is a method for offline updation. So this is offline updation. Do you see why? Because we are waiting till the end of the episode, right? Only after we reach time t is equal to capital T, only then I can update my GT of lambda. So that's why it's called an offline updation. I don't have to. I don't have to. I mean, I'm not updating my GT at each time step as I move ahead in time. Okay. Yeah. So it's 8 already. I see. I'll just wrap up the things. So this is the forward view. I'll just draw the diagram for TD lambda. Okay. Give me 2 minutes. I'll just wrap up. So this is how it looks. Okay. So the one step return has a weightage of 1 minus lambda. No, no. The one step return has a weightage of 1 minus lambda. Two step return will have a weightage of 1 minus lambda times lambda. Similarly, my three step return will have 1 minus lambda times lambda square weightage. Okay, so this is I'm getting from equation 6 only. Fine. And I keep going, making this go forward in time. Eventually, I get the Monte Carlo return here. Okay, and this is has a weightage of gamma minus t minus 1. Okay, so if I put lambda is equal to 0, okay, if I put lambda is equal to 0, only this value contributes, rest all other term becomes 0. So this is similar to a TD backup. And if I put lambda is equal to 1, then this is similar to a Monte Carlo backup. Reason being, all these terms become 0 except the last term. Okay, so this is an important point. To represent this, let's say this is the weight. Okay, and this is the time. Sorry, this is the time, and this is weight. So let's say this line here represents 1 minus lambda on the weight axis. This is the 1 minus lambda point. This is small time t. This is episode length capital T. So this is how the decay looks like. Okay. So beyond capital T, whatever I'll get will be the MC return, and everywhere else I'll have some one step return, two step return, n step return, all these contributions. Okay. So this thing corresponds to the three step return, right? So this will have a parameter of 1 minus lambda lambda square. Okay. So the weightage of each term corresponds to the area under the curve in this case. Okay. So this is weightage curve. Okay. One last diagram before we end up. Let's say, so this is just defining the diagrammatical view, sorry, it should say diagram for forward view of TD lambda. So I have state ST. I take action A, get reward RT. I have state ST plus 1. Further ahead, I have ST plus 2. Further ahead, I go on till I reach the terminal state. Okay. So I get reward of R T plus 2, R T plus 3. Here I get the terminal reward R capital T. Imagine if a person is sitting here. Okay. Imagine a person is sitting at state ST and he tries to look ahead in the future. So this is how, or this is what the forward view denotes. Okay. So he's looking one step ahead. He's looking two step ahead, three step ahead, or even n step ahead for that matter, and then taking a weighted average of all these instances. So this is the time axis. Okay. So this here is a representation for the forward view of TD lambda. Okay. So now since we are already running over time, I think it's a good time to stop. If I start with the backward view, it will take me really long time. So maybe we can schedule it for the next week session. So we'll continue from backward view for TD lambda and TD control, and subsequently whatever else is covered in that. Okay. So if you have any questions, please feel free to ask. Okay. Azhar Sheikh is asking, so can you please share the code for second example, Q learning Sarsa? Sure. Okay. So this is shared here. I'll also update. I'll also put a link to it when I update when I upload it on my YouTube channel. You should go watch my YouTube videos as well and subscribe to it if you haven't already. Okay, just kidding. It's up to you. If you have attended here, you no need to go to YouTube again. But okay, that's all I had from my end. If you have any other questions, please feel free to ask. Otherwise, I'll just end the session. Okay, thank you for your time. Thank you for attending and staying for 2 hours today. We'll meet again next week and hope you join next week as well. Thank you. Oh, okay. Bye. I'll stop the recording.